So first of all, thank you for coming. I have to admit, when this topic went in, I thought that I might speak to a room to 20 people. Now, hopefully by the end of this talk, it won't be down to 20 people. We'll see, though. I'll try my best. But may feel a little bit off topic. And as I get into it, you'll see that it's really more about, it's certainly in the context of high-speed networks, but it's really more ways you can screw things up and ways you figure out that you've screwed things up and how to make them better. So, and I'll talk about that in a second. So, legal, the company I work for, IBM, would appreciate it if you did not hold anything that I said against them. So, first, a little bit about me. I talked a little bit about some of my speaking disasters for some of you that came earlier. I've actually been a JVM and, interpreted languages guy for about 15 years now, working on a wide kind of variety of things at ahead of time compilation, bytecode verification, interpretation, mainly garbage collection, mind you. Although most recently I've also been looking at things like multi-tenancy and whatnot. You can see here that clearly I was just coming off vacation because I look all smiley and happy and well-rested and everything, whereas this is the usual working Ryan. And as I told some people earlier, my name is Ryan Champicone. That's how it's said. I won't quiz you on how to say it at the end, and I'm not even going to claim that I say it right, just the way my family happens to say it. So, what should you expect from this talk? Well, it's kind of, there's really two parts to it. There's sort of an introductory part that really lays out the current state of the world, where we're at, what you're looking at in terms of high-speed networks. It's not really an in-depth thing. I'm not going to go really deep on networks in general. What I am going to talk about is really a lot of the concepts, what's available out there, various speeds, and things to kind of keep in mind. Then I want to switch gears and say, okay, well, in the context of these high-speed networks, what happens when you actually start to deploy software that tries to exploit them, and some of the things that can happen to you. So you might have guessed this from my bio page beforehand, but I just want to lay out the disclaimer here right now. I am not a network expert. I am not a hardware expert. Not even close on either one of those counts. I'm a guy who, with teams of individuals who had a job to do, had to ship working software. These are the roadblocks we ran into, and this is how we got over them. All right? So that's really the context and the view that I'm coming from. So if I happen to say things or say, well, we kind of ran into this and we didn't know what to do, so we went around it, and you think you know the answer or you've got more insight than I do on that particular topic, come see me later. I'd be very interested to hear about it. But this is really me sharing war wounds and different head-slapping moments when you look at your code and realize there's no way this could have worked or performed very well. So. Most people who've done a computer science degree or computer engineering degree have seen this quote before, and it always makes me laugh because I tend to think about a station wagon full, complete with the wood paneling down the sides, hitting a speed bump and off into the air with tons of tapes flying out the back, and there's sort of that really actually there's a real connection between that and the experiences I'm going to talk about here. I mean, how many people have actually been on a system where you've maybe been working on single core or something like that, and your codes work great, and somebody says, oh, well, let's run on a 4-core system or something like that. And you think, no problem, it's going to be fantastic, and it's terrible. Like, it's worse than single core. Has anybody ever had that experience? Yeah, I ate crow once too. It was like terrible. So, the funny thing is right now is that networks, are just a thing for a lot of people. It's like it's there. You don't really think about it, right? There are differentiators: WAN, LAN, wireless, wired. But that's the way that people think about it. They don't think about it in terms of speeds or the problems that various speeds can cause, or say some of the APIs or facilities that are available to use these networks. How do those get in the way? What do they do? I mean, it's just a thing for most people. I need 2 computers to talk to it. Let's open up a socket, and that's the end of it. So, like I said earlier, I mean, there's more to it than that, and you discover this very quickly once you start to actually use higher and higher speed networks, that the bottlenecks, may well be in your code, and it may well be core design decisions that you didn't realize that you were making that suddenly affect your performance in tremendous ways. So, and really the bottom line here, which unfortunately I apologize, people at the back can't see, basically, look, things are getting higher and higher speed, but is there something that we can do to actually exploit it and not just use it? Okay, so there's a difference, right? How do you actually exploit something and really make use of it? All right. So just a little bit of history first before we get going. Network speeds have actually pretty much been proceeding or getting faster and faster over the years at a pretty steady rate. I mean, if you go back to 10 megabit Ethernet back in the 1980s or 1973, if you really want to be technical about it. But, we started out with a certain speed, and that was like great, right? Anybody who used anything like dial-up or so on just knows that this was fantastic. And over time, things have actually progressed and gotten faster and faster until we've gotten to the point. Now, people in homes or what have you, you're typically experience nowadays, it's 100 megabit or 1 gig E, right? That's your typical experience. You have the office, maybe 10 gig E, depends your office. But now there's something, Infiniband, which is actually even faster. Now, Ethernet is getting faster, but now there's also Infiniband, which is just, miles or light years, light speed fast equivalent to Ethernet in some cases. And so, networks are coming a long way, and it is actually changing. And I'm actually lying to you with this chart a little bit, because that's a logarithmic chart, and this is the reality of the situation now. So I apologize for people behind the pillar. If you look at the bottom, that's a huge leap for Infiniband, right? And I'm not even showing you the fastest Infiniband here. I've actually set up not numbers in order to prove my point. I've actually scaled things back a little bit. And like I said, Ethernet right now, 10 gig E, hits out to about here comparative to Infiniband. They are doing things to improve it, but Infiniband is just, ridiculously off the charts compared to Ethernet. Now, what does that mean in the context of the real world or everything else, right? One thing you always think about is, disk spinning speed, right? Never go to spinning disk because it's just way too slow, right? That's always been the thing. Anybody have the experience of taking their existing laptop and shoving in an SSD instead of their spinning disk? Yes, it's like a new machine, right? Yes, especially with file-based IDEs and so on. So this, and I haven't used, the numbers run such a wide gamut that I couldn't really pick one. So I sort of did a saw-off between a bunch of averages and kind of commodity hardware that you can say buy off the shelf or what have you. Infiniband's really interesting, right? If you look at 1 gig E, right, it's basically not even on the map. But if you start to talk about 10 gig E, sort of. You talk about Infiniband, right? I mean, we're talking SSD speeds here, basically, right? If not more. It depends the SSD and so on. And it's actually in the picture of something as simple as a Core i7, right? All of a sudden, your memory speeds versus your network speeds, they're not the same, but they're pretty darn close, all right? This gap is getting smaller and smaller and smaller. So, like I said before, this isn't a situation where you just want to use it. You just want to say, well, it's just another network. It's a bit faster, whatever. We'll throw our stuff down, and it'll just work the way it always has. We're getting at a point where you want to take a look at how your systems are currently running, how you're using networks, and are there better ways to actually use it, right? Network distance isn't as far as it used to be, right? So that's going to change the game, right? This is something completely new. And if you're coming from an old enough background, like something like IPX or so on, right, and you move on to TCP/IP, things got better, but they're still actually pretty terrible if you really look at it. And in the context, yeah. Oh, okay. Well, it's actually been around. So I'll get to that, like a small history chart when we move down. Right now, it's about 12 years old now at this point. So where is it deployed? You're typically going to see it in big corps, right? IBM, for example, right? Oracle. Oracle does some stuff with it too, and so on. So, yeah, if you do. So sorry, I should repeat the question, Mike. Where is Infiniband deployed? So. It's not some general network that you just kind of plug in at home. It is expensive, and it's typically used by big corps. Although it's starting to get pushed down, right? Starting to get pushed down. So, what chart? Should read my own notes, maybe. So this was a number of different competing designs that ended up merging in 1999. Now I'm going to take a very kind of quick overview of it, but you can think of it as it's basically a cable. So I joke about this. It's a cable between two machines, if you will, right? Like, it's a network, okay? But it's different. It's a lot faster, and the way you use it is a bit of a game changer. So it actually features a number of really important things. Really, really high throughput. Okay, you saw the chart previously. Throughput was just ridiculous. Extremely, extremely low latency. And one of the bigger things here that you end up seeing, aside from the scalability aspects, is that it actually guarantees delivery and quality of service. Okay, so you send something on Infiniband, it's guaranteed to arrive. Okay, unless somebody, of course, cuts the cable or something like that. But it's guaranteed to get there. It handles a lot of that machinery. Another interesting aspect about it is that it offers RDMA, right? Remote direct memory access. What that means is that you can actually have a chunk of memory on your machine, write a bunch of data out to it, and then say, oh yeah, I'd like to write this in this other machine's memory space at this location. And as long as both machines agree that that's okay to happen, you can basically have two-way transfer like this as basically I wrote here and it's going to show up on some other computer's memory. Really cool, really interesting, different way of thinking about things. Now, you can well imagine that, because of this, and that's really the last point, which is going to lead into a couple of different charts here, is that how you use Infiniband on, at the direct level is significantly different than how you might use sockets. Sockets are more stream-based, right? You write stuff and basically it's a pipe that basically stuff gets sent down, if you want to think about it that way. Infiniband, especially if you start to talk about RDMA, is basically like, no, that piece of memory over here is really local to me and I'm going to write to it. It's a bit slower than traditional memory, but it's really, really darn fast. Again, as evidenced by the chart. So there's no actual standard for using Infiniband. There's a de facto standard, and there are ways for upper level layer protocols like TCP/IP and so on to use it. And I'm actually going to get into that in these next charts. So, these pictures here are kind of generalizations, and if you want to surf the web and kind of read up a bit more about this, you can actually get far better detail and far better explanation than I could possibly give over the course of the next few minutes. But for Infiniband, if you wanted to use it directly, it really starts with your application at the top, and then you basically use a bunch of Infiniband services, okay? And this isn't like using a socket. You actually have to modify your application. If your architecture deals on a streaming type basis, you have to change the way that works. It's basically, write a bunch of stuff to memory and then say transmit. The way it works is not through a socket API. There's a bunch of things called verbs that you basically give actions to the Infiniband. You have to handle your own queuing and so on and so forth. But it's all right there for you. So the services are really kind of like this thin API to basically talk directly to it. And there's nothing in the way. This is actually really interesting. The kernel, libraries, and so on are completely bypassed when you use Infiniband. The really cool thing about that means that when you're transmitting stuff, when you say transmit, it now costs you 0 CPU, except to say transmit, right? There isn't a lot of work and machinery underneath to make sure things got delivered, divided up into packets and so on. Infiniband does that for you. You say transmit and you walk away, right? Basically 0 CPU burn. Okay, extremely, extremely low CPU cost. That's really, really important when you're talking about, big software that has lots of things to do. Spending a lot of time transmitting stuff is not what you want to spend his time doing. You just want to have it happen. And then basically it just goes directly to the device driver layer and so on. So right through, very low CPU cost. Now, you can use TCP/IP on top of Infiniband, right? This is called IPOIB, so IP over Infiniband. It basically allows you to use a socket layer API, okay? And this sits on top of TCP/IP, which basically in turn then talks to some IPOIB stuff that then says, oh, sorry about that, that's really Infiniband. I'm going to do a bunch of magic, hide all the details of Infiniband from you, make it all look like sockets, and basically use Infiniband, right? So the plus is that you could potentially get some of the speed improvements from Infiniband. Hooray. Except that now you have all this stuff and goop in the way that's faking things out and not really realizing that Infiniband's underneath. You're getting guaranteed of delivery services from the software layer, which is already being done by the hardware layer. And there's a lot of CPU burn going on here. When you transmit something, it's just like using sockets for all intent and purpose. All right, it's just at the last moment that it goes, oh, sorry, Infiniband, and switches over. Now, there's a third one, SDP, and the SDP, actually, you can look up on the net, just look up Java SDP, and there's tons of tutorials on how to get this to go. I think it's like the first hit right away. Same idea, right? Socket API, so okay, traditional code, you just slap on traditional code, except that it has much thinner layer in between that actually knows how to map the API from here directly down to the Infiniband core. And it, although it looks like a streaming API and so on, it gets rid of all the nonsense that goes on here that's unnecessary for Infiniband and just patches you straight through. Not as good as this, but it's a pretty good trade-off. And this diagram lies a little bit. SDP does make use a little bit of IP, like just in case you want to get technical, but it's not really important at this point, right? The important thing to really know here is that SDP, Sockets Direct Protocol, I should have said. And again, look it up if you're interested. It's a very easy concept and simple reads to kind of get up to date. It's a nice trade-off between not having to deal directly with Infiniband and verbs and all the queuing stuff and so on that goes on, and being able to use traditional socket API. All right. So I did want to cover just very quickly before I move on to some of the case studies, throughput versus latency. And the reason why is that I often find that you ask people, hey, do you understand throughput versus latency? And they say yes, and then you get them to explain it, and they almost do. And I admit I'm guilty of it too sometimes. I will say things that, oh yeah, well your latency, and it's like throughput, and that's because my brain is like a spinning top. But it's a little bit of remedial. Those of you who definitely know it, just bear with me for a minute or two. So imagine you've got a pipe, okay, and you've got a bunch of data units that you want to transmit. Right? So each of these orange squares represents a data unit, right? And you want to get that data unit down the pipe. Now that could be anything from a bit or a transaction or anything of the like, okay? So we'll just talk in terms of data units. Now, those things have to actually travel down the pipe to get to the other end, right? The time it takes from the beginning of the pipe to the end of the pipe is called latency. Perfect, right? Good. So a lot of you already know this. So an example of latency you might say, well, it takes 10 milliseconds, right, for something to get down to the other end of the pipe. All right. Now, at the end of the pipe, a bunch of stuff is coming out all at once, all right? A bunch of data units all at once. The rate at which the data units arrive per unit of time is called the, yay, all right, perfect. Maybe I didn't even need to go over this. So, for example, the throughput is measured as 10 gigabits per second here. Okay? Simple enough? All right. If that was a little bit too much for you, just take the shower analogy. Okay? This is usually one of the common ones, right? You've got a shower head, like a pipe, and then water comes out of the shower. The length of time it takes for a drop of water to get from one end of the pipe to the other is latency. The amount of water coming out at any one time is your throughput. So, throughput versus latency. The famous quote of you can't always buy latency. Sorry, you can't buy latency, but you can buy throughput. It's important to sort of note these types of things. Latency, the length of your pipe is the length of your pipe, right? It's very difficult to sort of shorten that thing. But if you think about sending data down a wire or something, you can buy more throughput. You can buy another cable to plug in. That cable will still be the same length, right? Take the same amount of time, but you might be able to push more and more data side by side down the pipe. And if you go back to the diagram, it's sort of the same idea. But your motivations for either going after more throughput or more better latency are often going to be defined by your own goals. So take, for example, a transaction processing system, right? It's going to care about throughput typically, how many transactions it can squeeze through per second, whereas the one user trying to get his trade through cares about the latency. Right? So there's going to be different motivations. All right. But when you have something like Infiniband, right, or these super, super high-speed networks, you can start to think about things differently. And this is going to lead into some of my examples. For something, the last quote here, for something like RDMA, right, if you've got such a huge amount of throughput available to you, it starts to change the game a little bit for you, right? Instead of being really smart about things, oh, geez, I got to compress the data to make it smaller, or I have to be really careful about which data I send, or, I wouldn't want to prime the cache down at the other end because it's going to take too much time to send all that data. You don't have to worry about it, right? Now you can do things like, well, just send the whole page. Yeah, I sent a bunch of extra data that I didn't need to, but I had the throughput available. Why not just send it, and then if it needs that other piece of data that's lying right next to it, it's already got it, right? this changes potentially the way you think about your own local memory layout and the type of data that you're transmitting. If you actually transmit more than what you are right now, maybe it makes you reevaluate how you lay your data out to make it as fast as possible to transmit the thing and then the next likely thing. All right. So networks are fast and getting faster. So I'd appreciate it when I talk about these examples if you didn't laugh too hard at us, but some of these things are just going to seem ridiculously obvious, but they always do in hindsight, right? You look at your code and you're like, oh, wow, who put that lock there? It was you. We've all, I've actually stood up and criticized code. I'm like, God, who wrote this? Ryan, it was you. So the first one's a really simple experiment. So I've sort of toned these down a little bit and kind of boiled it down to what the experiments were, and maybe not necessarily what we were doing, but it kind of gets to the root of things. The first one was really just a simple write. Okay, it was how long did it take to write a bunch of data kind of in a loop. All right, extremely simple. It was a single-threaded test. We were using 40 gigabytes per second Infiniband, and really we were just looking at network speeds. We were saying, look, we have this program. We know what it runs, how it runs on regular networks, but let's see how it runs on Infiniband. And actually, let's see what some of the upper layer protocols, the overhead, incurs on these types of things. So when I talked about SDP versus IPOIB and directly using Infiniband for RDMA, we just wanted to see the differences. We didn't know, right? We wanted to figure out, look, what happens here when you actually push a bunch of data down the pipe. And we did say, okay, well, look, Java's going to have some overhead no matter what. So let's write equivalent C programs, right, native layer, just to see what the difference might be, and in case Java itself is getting in the way. And being VM folks, we're actually in a position to be able to fix those types of things too. So it was really important for us to be able to see the differences. All right. Please tell me you can see that at the back mostly. You see the lines at least? Yeah? Cool. Thanks. So the blue line, first of all, this chart, the payload size at the bottom here runs from 1 byte all the way up through to, it's not listed here, but 512 megabytes. That's actually just the amount of data being written at once in a loop over and over again. Throughput is upwards, so up is better. The dark blue line, solid line, is the C version using IPOIB. The dashed line is the Java version using, it says DBB here. What I mean by that is direct byte buffers. We basically, NIO socket channels, and because we wanted to avoid JNI marshalling costs, so we used a direct byte buffer that's writing directly to native memory from Java and then sending it that way. All right. So this is just using IPOIB, and these diagrams actually all use the same format. Solid lines are C code, dashed lines are Java code. So I'll just sort of talk about it that way. The first thing you notice, okay, not surprising, is that the C code is initially faster than Java code. No surprise, right? I mean, there's a transition between Java and C in order to get down, to the kernel. The C code was written specifically for this one thing. So was the Java code, but it's really tough to get that optimization right down to the kind of the C coding level. It's such a simple program that it's really difficult. But see, I almost went down. You can see at a certain point, after about 128K or so, that things sort of start to even out, and then it sort of sticks together, and nothing changes. So the first thing that we ended up observing here, and through some of our research, right, looking up, Googling, trying to figure out why it's evened out, is it turns out that the IPOIB layer that you end up using actually, after 128K, stops sending the data en masse. It actually will start to carve the data up into 128K chunks and then send it that way. Okay, so at that point, the overhead is so high that Java and C end up evening out. Excuse me. Right. So that was like the first discovery. It's like, okay, well, IPOIB sort of has limits, and then it's it kind of evens out at that certain point. So that ends up being a bit of a problem, or something that you need to be aware of. We had to be aware of. All right. Let's try SDP. Right. SDP does not have the same level of overhead as the IPOIB stuff. Can we derive any? Excuse me. Can we get any more benefit? And we do, until we don't, right? So you can see both cases, C and Java, right? I mean, it just rockets right up. We're like, hooray, things are great, and then they're not, right? It looks like stock market line, basically, right? It's like everything was great and then not, right? It was just It was really disappointing. I mean, really disappointing to see that. So we weren't sure what to make of that. All right. So more work, more discovery, lots of different settings. What does it mean? What are we doing wrong? It's basically using socket API over Infiniband. How does Infiniband start to really be terrible at that point? All right. Brief little interlude. So I'm going to call this an interlude, and then there's this title 0 copy 64K boundary. Just ignore that for the moment. It will be made clearer very shortly. So when you're actually transmitting data from Java, okay, if you're using a classic Java.NET package, typically, and I'm going to kind of generalize a bit here, this is how it happens, right? You've got a byte array. You write data to that byte array, right? Data appears. You then copy that data over through JNI to the native space, okay, in order to be able to transmit it. Then after that, you end up copying from that native space into the kernel so that the data can actually be transmitted. Okay? There's a couple of things happening here. First of all, your data is getting copied at least twice. All right? That's really terrible. The other thing is that we've basically tripled the amount of memory required to transmit that data. Right? Now you might say, well, not really. Right? There's, this is on the heap. Right? We've already paid that cost, but still, that's 3 times. I count that as 3 times. Right? And there's a lot of CPU burn. All right? Copying memory is not free, not even a little bit. Right? GC background, believe me. Right? I wish it was free. Not. So there's a lot of things happening here in the traditional system. Now, all right, but I did say we were using direct byte buffers, so directly writing to native space with SDP. So what was actually happening here? Well, the obvious shortcut. We have an array in native space. We're writing the data directly from Java to the native space, and then that's being copied, then transmit. All right? 1 copy instead of 2, not bad. Cut the memory use down to 2x instead of 3x. That's okay. And there's a lot less CPU burn. All right. Pretty good stuff. So that's great, Ryan. But that doesn't explain why there was this huge drop-off on SDP. Well, here's the difference, right? There's this thing called 0 copy threshold in SDP. Right? If your payload is greater than 64K, when you use SDP, you write data, say 128K, and then that memory is registered, okay, with Infiniband for RDMA purposes. So what it says is, I'm not going to copy this to the kernel and transmit. I'm actually going to register this memory in place, okay, and use RDMA to transmit that directly. Sounds fantastic. It's exactly what we want, right? Write it once and then it just appears in another machine space. Sounds excellent. But it's not, okay? Because SDP on every transmit will actually register and unregister the same memory, and this is extremely slow to do. So slow that it outweighs the benefits that Infiniband RDMA would actually give you, okay? And it actually craters your performance. So you go to transmit this, and then of course, there's the super expensive unregister as well, which is not quite as expensive, but still. Now, I apologize for the bug on my slide here. There should be no copies before it's transmitted, but the register and unregister is extremely, extremely expensive here and kills any of your performance. So going back to the original chart, you can see here what's happening is that at 64K, everything's great. You're getting tip-top performance. We seem to have plateaued, which is a little disappointing, but still, you're getting a lot better than IPO-IB. The 0 copy threshold hits as we move to 128K threshold, and boom, your performance drops. There's a certain level of overhead. You end up recovering a bit of that performance, but not to the point that it actually really matters. All right? So something to be aware of. Like, these are the types of things. Hey, look, faster is better. Maybe not. Maybe you're dealing with different problems, right? So there's something I want to. Oh, sorry. Yes, one more thing. I've jumped a bit ahead here. So the last thing we tried was just using RDMA directly. So same idea, use a direct byte buffer, write straight to native memory, and use RDMA ourselves. So we've got a chunk of memory that we're going to write to. We just register that once at the beginning, and we reuse that to write the data back across. Really fast, faster than SDP, and there's no degradation. And quite frankly, although the graphs make it look even, C is slightly ahead of Java, but only slightly. Okay? So this, I mean, this is a really nice chart to see, right? Scales nicely, right? We keep adding payload, no problem, right? So it's really good. Now, the problem with RDMA, using the RDMA is that we had to write a lot of the infrastructure ourselves. It's not particularly hard. We're systems guys, not a problem. But for the average person right now, or the average Java developer, this is still like a little bit inaccessible to them. Right? So this is the kinds of things that we're like, well, okay, we got to figure out a way to fix this and make this a bit more accessible to people. Just a little note about that zero copy threshold, the 64K. You can actually adjust it on STP. So you can actually set it lower or higher if you want. So we wanted to find out, well, okay, well, what happens, right? Can we actually improve the situation or not? It turns out you really can't, okay? Even if you set the copy threshold lower, you end up with this sawtooth pattern, and really, if you set it to a lower amount, you'll get this, you'll hit your peak, you will drop significantly, then you come back up, and no matter what threshold you set it at, it seems to always return to about the same point. I don't really have an explanation for that. And you might actually say, well, look, why is there a zero copy threshold anyways, right? Like, what's the point? You have to think about it. If you have a 1 gigabyte buffer that you're writing to, and you want to actually transmit, you certainly don't want the kernel trying to allocate a gigabyte within itself, right? It's typically not even possible. It gets to the point where STP says, look, I'm not going to force the memory allocation to occur. I can't. So instead, I'm just going to go ahead and register it and unregister it for safety purposes. But in the end, it turns out, so we played around with this for a little bit, and it turned out that, look, 64K, the default setting, actually turns out to be pretty much the sweet spot. You peak, you tend to plateau. We didn't have much more than that. So something to be aware of. Anyways, again, not an expert, just telling you what we ran into and what we saw and what we observed. If you actually want to experiment with this, you'll probably see the same thing. All right. So yeah, the beauty of some of these things, of course, like what do you see here? It was nice, IPOIB. SDP is actually relatively simple to set up. I mean, again, just Google that, super simple to do. It's really easy to set up, but you're certainly not getting the benefits, and there are certain limitations as well you have to watch for. You can get increased speed, of course, as we saw from the graphs. You just have to watch out what you're doing, your payloads and so on, what your expectations are. If you really want to go hardcore, you can certainly get huge advantages, but you've got some native stuff to write. I wouldn't call it it's not trivial, it's not rocket science either. You just have to be aware it's a different way of doing things. And of course this is the first indicator that there are hidden gotchas, and that's purely from the network point of view. All right. All right. We're 30 minutes in, I got about 15 minutes here. So, all right, we think we know everything, right? We ran some tests, great, we got it, no problem, right? And that rest should be easy. So the next experiment we did was we took the orb, using RMI and whatnot, and we said, well, look, how does this perform over Infiniband? Okay, this is sort of a different approach. This isn't, we're not going to be writing data, just writing data. I mean, we're going to be doing stuff like marshalling data and transmitting it and so on. What are the problems? So the test was really, we just want to send different size packets through the, different size payloads rather through the orb. We're just measuring the time required to complete this test. It is a multi-threaded test. We had 500 threads doing this all at once. We were just measuring the time to complete, not the most scientific thing, but it was at least a measurement that was sort of interesting to us. And what we wanted to do is we wanted to say, well, look, what's the comparison between Ethernet to SDP and IPOIB using Infiniband? I've got the list of conditions here. We're using just a byte payload. That actually changes things a little bit for those that understand the orb, but still it was an interesting experiment. The real expectation here, again, bottom line, I'll read that for people at the back. At this point, we said, well, look, we've got the Infiniband thing figured out. So, we're realistically expecting to discover a whole bunch of performance bottlenecks in the orb. And this side of it this is how your code can get in the way of performance, particularly in high-speed networks. And I talk about Infiniband a lot here, but I mean, this can also apply to, even 10 gig networks, right? This is the same sort of thing. And we actually do see benefits as well from some of the stuff that we discovered. So here's Ethernet. Here was the experiment. We ran it. Okay, pretty standard looking graph. Down is better. This is time to complete, right? So up is more time, therefore down is better. Not the most scientific, like I said. And again, payload size. What's the size of the bytes that we're actually shoving down the pipe? Okay, standard graph. Run it with SDP. And better, but not what you'd want, right? And that's a lot of money for not a lot of wind. So, okay, what was the problem, right? And what were some of the problems that we discovered? And here is where you're going to go, oh my word, you don't write code this bad, do you? And the answer is yes, we do, and so does everyone else. And it's okay. We'll all meet by the bar later and discuss our problems. All right. So what's the first ridiculous thing that we ended up finding? And again, this may not be you, but it's the kind of thing that you're going to find and you're going to have to look for. So just kind of be aware, be ready to laugh at yourself, because who else will other than everybody? So we have a byte array we want to send, and we want to squeeze it through the orb. All right. So really bunch of bytes. Let's write the data. All right. So how it actually works, though, and generalizations, is that the orb has an internal buffer that it actually uses for transmission. So it takes the data and says, okay, well, I need to send this across. So what I'm going to do is I'm going to push that data into my internal buffer, and then I'm going to send it across. Okay? Very general answer, blurring some lines here, but this is basically what happens. Well, I've actually drawn this kind of to scale because the internal orb buffer is 1 kilobyte, and let's say we're sending a 2 kilobyte byte array down the pipe. You can see the problem, right? We end up having to take that byte array and split it conceptually into 2 1 kilobyte chunks, and then basically we pick this thing up and then we copy it into some internal transmission buffer that we then go and transmit. Okay, completely ridiculous, right? Right, and this, oh, hey Kurt, how you doing? I didn't see you there. So you will see this kind of stuff all the time when you look in your code. Right? I see some smiles in the back, and hopefully it's not like, wow, that guy's an idiot. It's actually more like, wow, we've been there too, right? So you end up seeing like really simple stuff like that, and it's a byte array, folks. Just take the byte array and start sending it directly, right? That's simple, right? So these are the kind of things that we just weren't optimizing for, and it was like simple fixes in order to derive better performance. Now, you can actually, that was byte arrays, but speaking in kind of general terms about, marshaling the data across, what we ended up finding was that, okay, this 1 kilobyte thing was actually getting in the way of the Ethernet stuff, and 3 to 4 kilobytes was actually sufficient to kind of max out your performance. Anything larger really wasn't getting you anything, right? Now, for SDP, does anybody want to take a guess what the best buffer size was? Oh, I think I heard it. 64K, exactly. Right? The 0 copy threshold. Anything larger, right? We started just to go max it out. So it was just a lot better to avoid, the hairy situation of having the memory registered and slowing you down. So if we kept that buffer at 64K and transmitted 64K chunks, performance was excellent. All right, that's the big one. Garbage collection. I went and admitted I was a GC guy beforehand. So, if you want to throw vegetables at me later, it's fine. And this isn't a GC talk. I'm going to try and make this as quickly as possible. Imagine this is your heap, okay? And you have a bunch of allocated memory. That's the orange spots. And the way memory ends up working is there's a lot of fragmentation holes throughout. So there's free memory here, here, and here, and so on to accommodate different types of allocates. Well, one of the things about increasing the buffer size as well that we had to sort of balance out, and it's nice that the 64K one ended up working out well for us in this case too, was that you can actually start to get into situations with large enough buffers that thing is actually bigger than any of your available free memory. So you can have enough free memory if you summed it all up in order to allocate it. But unfortunately, you don't have one contiguous chunk to wedge this thing in. Guess what that means? A premature garbage collect, right? You're going to have 30% free memory on your heap, and a GC is going to kick in, and worse, perhaps a global compact. So when you start scale out your buffers and so on and worry about what should make the most sense, one of the things you have to account for is how big your system is. Is your test environment mimicking what's actually going to happen in the real world? And are you going to be incurring a ton of GCs that you didn't necessarily have to do? And is that going to hurt your performance more than shrinking your buffer a little bit so that you don't incur these types of problems? All right. Last ridiculous problem. So these were all cumulative, and there were a lot more, but these are sort of the ones that my management felt fit for public consumption. That's a really simple diagram here. So we actually have, from the client and the server side, we actually have, it's 500 thread test, right? So we have a bunch of threads running as a test. Like I said earlier, there were 500 of them. 500 of these guys are actually trying to communicate with the server via the orb. Well, guess what the initial configuration was? 1 connection. So stop laughing. Yeah, I told you. See, are you laughing at me or with me? Because I can't tell. So these are the types of, you look at this and you're like, well, what were we thinking, right? And we've been living with this for how long? So it's just ridiculous, right? So, super highly contended resource ends up being a nightmare. You just couldn't saturate the channel anyways. You got 500 threads with one little straw that everybody's trying to cram their stuff down through. Ridiculous. All right, so let's play around a little bit, right? So we said, okay, well, look, we have 500 threads. Let's give it 500 connections, right? So that was terrible. Yeah. Hey, that'll work. No. Just a disaster left and right. This did not work, okay? Resource nightmare, completely context switching nightmare, and so on and so forth, did not work. What we ended up finding, actually, and to quickly kind of zoom through this, 10 connections, or about anywhere from 2 to 5% of our actual number of threads, turned out to actually be the best sort of number. It was the best situation for this test, to be clear, for us to be able to saturate the pipe and minimize the amount of context switching that was going on to basically delay transmissions and so on, have the right level of contention at a lock. I just said that, the right level of contention at a lock in order to maximize our throughput, okay? These are the kind of things that you end up sort of looking for. It's sort of weird how some of this math ends up being kind of fairly common in a lot of cases, depending on what you're doing. That 2 or 5% is certainly not a rule of thumb for everything, but for a lot of things that we ended up doing and experimenting on, that seemed to be the one for us. So, you kind of end up looking for these types of things, and you see them, and they actually help you pick better defaults to start with, too, in a lot of your software. All right. So a bunch of those, silly things and more occurred, and we, went and hammered them out of the system. And so, going back to the original graph, this is what we had. And I apologize for the shift. It's just the legend got bigger. And this is the SDP with the new stuff and all the changes. Now, I won't lie to you. Some of those changes also affected the Ethernet thing, which unfortunately I don't have on this graph. But the point is that we got significantly better. I will also point out that 64K threshold and increasing the buffer was really the bulk of the win. Okay, but there still were other things that actually gave you that extra few percentage points that really helped out, right? And you ask any performance person who's done gotten a system in place, 1% is gold. Okay. You get 1% out of a system that's one that's actually had all the dumb things cranked out of it. 1% is worth absolute gold. Okay, so a lot of these little changes are really, really worth it in the end. So good, not stupendous, but a lot better than it was, right? And that's just by fixing silly things, right? Your code. We ran IPO-IB as well, just for grins, just to see where it was, just to make sure everything was the way we expected it. I apologize for the light blue line. It's about where you would expect it to be. So, from that experiment, it's quite simple, right? We don't all climb into race cars and drive to work at 300 miles per hour. We love to, except that the odds of us actually getting there in one piece is pretty low. And I'm not saying that you should do things slowly here, but it's a matter of just stepping on the gas, right? Is not it's not that simple, right? You wish it was, but you have to watch out for a whole bunch of other things that are in your way before you can actually go that fast. All right, that's basically the end of the talk. I think I really said a lot of this throughout, and so conclusions are a lot about just sort of repeating yourself. There are faster solutions out there, but a network is not just a network; it's a lot more. And there's a lot of ways that you can go out there and exploit it and use it to go back and find the problems in your code, right? Like I said, it's the old problem of you ran on one CPU and then you ran on 4 and your code got worse in performance. This is the same idea. It's getting to the point where people just don't think about the fact that their networks, that's the same problem. Okay, networks are reaching the point where that's the same problem. You have problems in your code likely that you need to ferret out in order to really maximize the advantage that you can have. And on that, so Yeah, I will take questions. What I will say, though, is that that's the end of the talk. Thank you very much for sitting through it. I'm glad I don't have 20 people left like I said at the beginning, so thank you for enduring this. If you want to leave now, please feel free. Just do it quietly while I field some questions, and thank you very much for your attention. Appreciate it. Sorry, question at the front. Can I elaborate on the... Yeah, so, okay, so the question is, can I elaborate on the internals of Infiniband? I'll maybe start over. I'm not a network expert, so I can talk to you offline about what I know, okay, but it's what I know, all right? Quite frankly, if there's somebody in the audience who knows more, I'd be happy to turn you right to them and say, talk to them. For us, it was just, hey, look, it's cool, new, and it's fast. Let's try it out, and it wasn't. So, but that having been said, a quick Google. There are tons. There's one simulator. We'll exchange email addresses. There's one PDF. It's like 50 pages long. And if you want to learn anything about Infiniband, you don't know a thing. It's 50 pages. You'll have it read in like an hour, and you learn so much. Right? Not composed by us, but it was well worth the read. Go back which slide? Oh, 51. Okay, in the meantime, well, Mr. Performance. Okay. Go ahead. Okay. Oh, sorry, who? So somebody else had their hand up? Right there, go. Yeah, direct use, right? Yeah. So if you get rid of SDP, the reason why you want to use, say, something like SDP is all your stuff is socket based, and you don't want to change your stuff, but you want to use Infiniband. So something like IPOIB or SDP is basically just keep using sockets, except we'll use Infiniband and try to exploit Infiniband for you. So at the top, no, actually, when I said that, that was so Infiniband services, they're not a Java thing. It's just a very thin C layer that basically knows how to talk to the Infiniband. Right. So yeah, there's no, as far as I know, do you know anything that's Infiniband direct Infiniband-based protocols from Java at this point? I don't know of any. No. Okay, so. Right. So yeah. So the short answer is nothing available yet. But we have a VM. Oracle's got a VM. You can expect something in the future. But there's no true standard at this point other than how you talk to Infiniband, which it's unclear if that's how you want to talk to it from Java. I would say it's not, but that's one of those things where exercise for the listener. Take a read. The conceptual points about how it works, how you have to end up watching queues and so on, it's very easy to pick up, and there's some very simple literature out there that really explains it kind of at the level that you want without becoming a network expert. Go ahead.
Do you know why it went up again?
So, all I can say, we didn't really investigate that much. All I can really say is that there's a huge hit, but then the non-copy aspects start to gain you back, right? Because you've pinned the memory effectively, right? At that point. So it's a huge cost to pin the memory, but then as you transmit more and more, you can start to gain that back. But then the weight of that ends up hitting a max. I'm really blowing smoke here at that point. That's what we believe was happening, but I'm not necessarily 100% certain.
Are you taking into account with the experience of
No, actually we didn't. So that's there. Another. Oh my gosh, yeah.
At some point in time, you can plateau off.
Yes. Up there. You were talking about this here, right? Though. Okay, so that's what I was answering there. But yeah, at this point, yeah, you could.
Because when you get into like 4 to 16 meg and stuff like that, depending on the payload size,
yeah.
depending on what your rates are, when you start getting that big, then you're just going to saturate the bus.
So that's an excellent point.
I guess the thing about that stage, then that will be which on a practical program. This is a benchmark doing nothing but writing.
Yeah, this is not a real,
You can saturate your memory bandwidth just on your benchmark, right?
may or may not. Yeah.
Will have an impact on say its object allocation rate, which might be probable.
Right.
By you looking at your memory bandwidth doing.
Absolutely. I was going to say that Java is memory, which causes a real problem for Java, right?
So you'll probably get, in this case here, when you're going from back, you'll probably be looking at your higher corruption rate.
Right. Good points. Anyone else? Oh, sorry, over there. Yeah, not anything that I have here, though, unfortunately. There's not really... I actually not anything that I can legally give you, unfortunately. Apologies on that one. My company won't let me actually divulge. This is why I have to strip throughput numbers off the side. Yeah, I'm sorry. Right, because somebody's going to read something into it and legal action or something. I'm sorry. I know. Hey, hire me, whatever company you work for, and then I can Are you looking for a job? Whoa, is this still being recorded? Well, they'll actually be if they aren't. Yeah, Chris, do you have the answer for that? Okay, they'll be on SlideShare. Okay, yeah. So you have my name, or you can look it up on the. If you don't end up seeing them, just drop me a line, and I'm happy to hook you up here. Sure. It's quite rare. I maybe didn't understand the question then. Are you saying? Sorry, is the question? Right. So I might say there that you can derive wins from high-speed networks. Okay. It's pretty clear that things can be better. They will not be the best that you can possibly get, so you need to evaluate the cost benefit versus what it's going to take for you to put that in, and that when you do use these upper level protocols, that you have to be aware of some of the limitations that exist. So I showed IPOIB and SDP and some of the gotchas that you've got. The point is that as much as it may look the same, because it sucks, it's not. Right, and just so be aware of that. If that's how you're going to exploit it and you think it's beneficial, great. Be aware that there's things to be aware of.
The Infiniband should use some kind of protocol, right?
No, so Infiniband has its own transmission guarantees of service and so on protocol. You can slap down TCP/IP on that, like IPOIB, but it's pointless. Okay. Yes, absolutely. And there was one more. This is my last one, folks. I got to clear out. So. Right. So the question is who's going to use it? I'm not going to get into what from a customer point of view. I'm not going to start to divulge who customers are doing what. But anything where it's you need. You can think of any transaction system, right, that requires incredibly high throughput and low latency. So things like trades or so on are huge parts of that. So this is in use, absolutely. But from a Java point of view, not a lot of people are really they're not at that point yet. It's just sort of starting to enter into the consciousness. Even though SDP tutorials for Java have been around for a number of years at this point, you can look it up. It's very easy to kind of look it up. But there are certainly use cases for it. Poor choice of words. It is certainly in use by our customers. Absolutely. Okay. Thank you, folks. Appreciate it.